did we have to assume? What else did we look at? There was another big thing that we dealt with. The standard error. And what did we say the standard error was?
The mean and the mean.
Divided by the square root of the count.
Standard deviation of what?
Square root of the population.
Standard deviation of the population divided by the square root of sample size. Or n. Huh? What do you say? Why do I keep saying that?
No, before I used to say sample size, now I just keep calling count.
So, yeah, it's the same sort of difference when I use it. Now, what did I say about the standard deviation of the population?
It was the same as the standard deviation of the sample.
It wasn't the same as the standard deviation of the sample, but I also said that a lot of times we won't know that. So we got to make a alteration. So when we start doing this, we're going to construct confidence intervals for means and proportions. What's a proportion? Parts of a group, right? Okay, so we're going to learn to deal with both of these. Our basic method is always going to be the same. We're going to need to take, if we're doing means, we take the mean plus and minus the, and this is where Rachel the other night said that I used the word margin instead of error-bound margin. Because we're going to start talking about, when we talk about proportions, the book labels that as error proportion margin, EPM. And there's other margins that we use, so I just tend to use the word in general, margins. Okay? You're always going to take something plus and something minus. The variations are going to be how we get those margins and how we get the standard errors. So when we start doing this, the first things that we look at when we start doing confidence intervals is we ask ourselves, is this a mean or is this a proportion? If we decide it's a mean, and we actually use these two questions the same whether it's a mean or a proportion, we always have to say, what's our confidence level? And once we know the confidence level, we then know the, what's related to confidence level?
Alpha.
Alpha. Sometimes we'll actually give you the alpha and we want you to give us the confidence level. So it doesn't, you have to pay attention whether I'm going to give you alpha. If I say use an alpha of 20% or a confidence level of 80%, I basically have said the same thing. So you got to understand those go hand in hand.
But confidence level is the percentage. The alpha is whatever left over from 100% of that percentage.
Right.
Yeah,
Okay.
this is for the mean.
This is for both of them.
This is for both.
This is actually for both of them. Confidence level, alpha. Okay. Then the next question I always ask myself is the standard deviation of the population known or
Unknown.
unknown? Well, we already did it if it was known. Okay? And based on the answer to that question, we go, do we use a normal Z table or do we use a T table? And here's where sometimes you'll find some differences in some books and how some people sort of deal with this and how they do that. If the answer to this question is the standard deviation of the population is known, what table were we using?
Z.
Z table. So if the standard deviation of the population is known, we use a Z table. If the standard deviation of the population is unknown, we use the
T table.
T table. That's how the book does it. Actually, in reality, is if we can sort of ask ourselves a second question and say, what's our N? And if the N is big enough, I can forget all about the T table and just use the Z table. But for now, the way that the book does it and everything else is if the standard deviation is known, we use the Z table. If the standard deviation of the population is unknown, we use the T table. Which means you have to be able to go and look up a value in the table. What helps, what determines what value you find. And the way we use the different tables, the T table is actually easier to use than the Z table. Okay?
I like easier.
So that's the aspect behind that. And the second question is, how do you calculate your standard error? That's going to be the big difference. And with a and then you have to calculate the EBM. But you can see with the proportion table, with the proportion, we're almost always going to use a Z table. So we're not going to worry about that. But the big difference here is how you calculate your standard error. So those are the big things that you have to deal with. Okay. Now, what we tend to remember is, when do we use a Z table?
If the standard deviation is known.
If the standard deviation of X is known. Or if we have a really big N.
What is big?
Huh?
What is big?
For this case, over 100. In most cases, we'll say, some people will say over 30.
Wow.
Some will say 35. Some will say 40. It varies.
Use the Z table if the standard deviation is known.
Okay, you use the T table if this is unknown. So that's the big difference. And then how you have to calculate those. So I'm going to walk through a couple of examples real quick. Where'd it go? Now, you guys can follow along. I think I set this up so that you can go in and go to WebAssign. And you should find something that says in class 2. CIN class 2. And if you click on it, it should open up for all of you and use the exact same numbers for everybody. I think I forced it to use the same numbers. So hopefully you have the same numbers I do. So if I read this question, what does this question, what's this? So it says what? The standard deviation of the weights of elephants is known to be approximately 15 pounds. What's that telling me? Huh?
That,
It's
from the
proportion.
mean.
No. What's it telling me?
The standard deviation
Of
of the weight of elephants
is
known,
It's 15
which is
pounds.
15 pounds.
it's 15 pounds. So what are they talking about?
Use the Z table.
Okay, what are they talking about?
Standard
Standard
deviation.
deviation of the weight of elephants.
Of elephants. If I'm talking about the standard deviation of the elephants, I'm talking about what?
Weight.
The weight of what?
A sample.
A weight of an elephant.
What about the elephant?
What's it?
They're 15 pounds.
No, from the mean is.
Which elephants am I talking about? What elephants am I talking about?
You don't know.
Look at all words.
No, it's talking about,
Newborn.
No words.
no, it's talking about, well,
Yeah.
the,
newborns are weighed.
but it's talking about elephants,
Yeah.
Yeah.
That's what you
Yeah.
which are, if I'm talking about elephants, am I talking
Multiple elephants.
all elephants, which are what?
A population.
A population.
I was half my sample.
Okay? See, when they word it like that, they're talking about the standard deviation of elephants, which implies they're talking about the population.
It's a plural.
Okay?
Plural.
we wish to construct a 95% confidence interval, which means my alpha is,
5.
5. 2.5.
2.5.
no,
What?
close,
What?
5.
close,
5%.
0.5.
5%, or 0.05.
0.05.
5 is a big number,
Yes.
okay? So see this is where, you guys wanna grab little things, but you gotta keep the details in there that keep you leading to things. For the mean weight of newborn elephants, then they say they're going to do what? They take 50. What would that be?
Sample.
A sample, because that's not all the elephants, I'm just taking 50 elephants, right? And they are weighed, and the sample mean is 244. So we're going to use, by central limit theorem, we're going to say, we think this is the mean of the population. It's the mean of the sample, but we're going to use it to estimate the mean of the population. And it says that the standard deviation is, what's that the standard deviation of?
One elephant.
No,
The sample.
it's the standard deviation of the sample. See, this is why I'm saying you gotta pay attention to what you're doing, because, see, here they said standard deviation is 15, and here they say the standard deviation of the sample is 11. So we know that the standard deviation of the population is 15. They gave us the standard deviation of the sample. That may or may not be important in this particular problem. Since we know this is not got as much importance to it as if we didn't know this. Okay? So that's where it sort of comes in, that you have to be able to identify where each piece comes from. This is why I was trying to get you to think about whether it's the population or the samples. Now, basically, we got our normal table. What number goes here?
244.
244, which is the
Mean.
mean, and also the
Median.
median. And when I'm doing this problem, this is sort of how I would probably sort of look at it, is I sort of have to look at that. What number are we going to put here?
50.
No,
Oh, what?
we're constructing a confidence interval, so the number that goes down here
The low bound.
is going to be the lower bound. The number that goes here is going to be the upper bound. And to get the lower bound and the upper bound, we need the error bound. So see, I need to calculate this before I actually do this top part,
Okay.
okay? What's my confidence level?
95.
95%?
We have to put the percent down.
It's got the percents.
I don't.
What doesn't?
Okay, so it says to do what?
Oh,
Round everything to
2 decimal.
2 decimal places. So I should write it as 0.95. Which means my alpha is 2.5. Now, they don't give us some information. Before we can finish this problem, we need 2 more things. Before we can get this, we need 2 things. How do we calculate? How do we get the error bound?
The standard error
It's standard error
and the Z.
times
Z score.
the table value,
Table value.
which is found by alpha divided by 2. Now, we can use the table to get that. So if I use the table to get that, and somehow or another, half of my table disappeared on me today.
Yes, because you gave it to me.
I didn't give it to you, you just sort of snatched it from
No,
my
I asked to.
Okay, so what do I look up in my body?
9.95.
97.5.
And
9.
I can either look up 97.5
No, 97.5.
I can either look up the Z for 0.975, or I can look up the Z for
0.05.
close,
2.5.
0.25. Because this is my alpha divided by 2. This is the high end and this is the low end. And the absolute value of these numbers, the absolute value of those numbers will be the
One.
same. One will be negative and one will be positive. I tend to look up this one because I tend to use the negative side of the table because it's first.
No.
So when I look that up real quick,
1.96.
so I just have to look that up in the table. Well, is the standard deviation of the population known or unknown?
No.
No.
Known. So if the standard deviation of the population is known, I use the
Z table.
Z table. Okay, do you see? See, these are the things that you have to run through.
Yeah.
Okay? So there's my Z value. Now, how do I get my standard error?
Take the standard deviation,
Of
11,
Population.
the population
population.
divided by the
Square root.
square root of n.
50.
Oh, no.
So the standard deviation of the population is 15 over the square root of 50.
Oh, right.
Okay, see, not the see, that's why I gotta be careful that it's talking about two standard deviations. I gotta make sure I'm using the right one.
Right, right.
Okay, but which one, how do we know which one to use and what not to?
The standard deviation of the
Elephant.
elephants. Is it talking about a group of elephants?
No, it's not all of them.
It's talking about all elephants. If I'm talking about all elephants, I'm talking about a
Population.
population. See, this is why it's important to understand the use of words.
So we don't use it first.
Down here, it says the sample mean is 24 and the
Sample.
sample standard deviation is 11.
Isn't the sample standard deviation the standard error?
No.
No.
It's close, but it's not quite.
Oh.
Okay? So I need that number so I can sit there and go 15 divided by the square root of 50 is 2.12132. So I'm going to multiply those two numbers. So 2.12132. And if I have my calculator and I'm using my calculator, I will normally get the standard error in my calculator first and then multiply that. I'll just leave that in there after I do the division, do the calculation in my calculator and multiply by my table value. And that gives me 4.15778. So my error bound margin is what we just calculated. So in this case it is, what did I say?
4.15.
4.16. Now, how do I get this number?
And
I add 4.162
mean
to the mean, so I get 2. This one's easy to do. You should be able to do this without a calculator. 248.16. Since this is a whole number and I'm just adding that, it's kinda, I just add the 4 to the ones column and keep that going. And this number would be what? This one's a little harder to calculate.
$239.84.
$239.84. And we're done with this problem. Except for we haven't filled in a couple of blanks. What do we mean when we write this up here with a couple of parentheses on either side? This is a interval. What number goes here?
Lower.
Lower bound. What number goes here? Upper bound. So Control C, Control V, Control C, Control V. And did you guys hit the submit button and everybody got it right? Now, a couple of other things. I can sometimes cheat and use technology.
We love it.
Okay. If I want my T value, yes.
I'm really stuck on where that 50 came from.
What 50?
There's a 50 there somewhere. That one.
The count.
No.
That's problem.
Okay. Okay, that helps.
That's my sample.
Got it.
50 newborns. Wasn't magic. I didn't pull it out of.
I thought you did.
That was my sample size.
So if it was the count for the population, it'll be capital N?
We're normally not going to have the count for the population, but yeah. Normally, if it's a population, we would use a capital N. That's one of those ones where you'll hear people just say count, and you have to understand whether or not they're talking about a population or a sample. Because I will use them, I won't distinguish what's the count, what's the samples. That's why sometimes when I'm working with this, I actually say sample size instead of count.
Gotcha.
Okay? Because I'm dealing with the sample.
That makes sense.
Now, we're going to change this. If I did this problem and they didn't give me this, they didn't tell me this up here. They did not tell me that. There's only 2 slight adjustments that we make. One, if we don't know the standard deviation, we can't calculate the standard error. So when we're looking at these, let me see here. Okay. When I'm looking at this, the standard error is calculated, and when I can write the symbol, I use this symbol for standard error, which is the standard deviation of x divided by the square root of n. And a lot of times you will see that I just write it like this. Now the aspect behind it is you will learn that we use standard error in a lot of different situations.
Bless you.
And standard error changes depending on what we're looking at. Now, if I don't know this, I have to use an estimate for this? Well, what do you think we can use to substitute for this if we don't know this?
Standard deviation?
Huh?
The regular standard deviation?
What do you mean the regular standard deviation?
Just the regular standard deviation of the population.
Just a variance.
No, because that's what this is.
I know.
That is the standard deviation of the population.
We don't have the standard.
If we don't have the standard deviation of the population, what can we possibly maybe want to use as a substitute for it?
Sample.
The standard deviation of the sample.
So how would we have that? Can we do that? Yeah.
Because if we collected the sample when we calculate these, we know how to calculate the standard deviation of the sample.
So normally you would have the standard deviation of the sample compared to the.
You will
sample.
always have the standard deviation of the sample because you can calculate it.
Right.
If you have the data to calculate the mean, you have the data to calculate the standard deviation.
So you're gonna give it to us in the question?
Well, remember when I gave you when we did the dead rockers and you calculated the mean? You also calculated the standard deviation, right? There you go. That's it.
Okay.
That's the standard deviation of the sample. We didn't have the standard deviation of the population of dead rockers.
Right.
So see, in that particular case, we wouldn't have had the standard deviation wouldn't have been known. So the only difference in that formula is that if we don't know the standard deviation, we got to figure out something to use in place of it. So we're going to opt to use the standard deviation of the sample. However, when we do that, it causes us some other grief. And because of a guy that used to brew beer for Guinness, he makes life a little bit easier for us back in the 1500s or 1500s. This guy brewed beer. He worked for Guinness, the brewery, and the agricultural. And he had to do a lot of sampling to make sure that the beer was always good and that the crops they were using was always good. So he had to discover something else. What he discovered was if things were kind of normal, there was a slight variation to it. And instead of using the normal Z table, which he knew about, he developed a whole new table. And because he was working for Guinness at the time and it was illegal for him to publish information under his own name, he gave it to one of his students. And the student published it as Student T. And that's how it got its name, as the Student T table. Because the guy who actually developed it wanted to remain anonymous, so he gave it to one of his students to publish.
So he's still anonymous in history?
No, everybody knows who it was. Except for Guinness Brewery back in the 1500s. And they gave us a new table. I'm going to give you a new table. Now, this table is kind of easy to use because I printed off a nice one. That's a little bit easier to use than some of the other ones. Because this table, basically, instead of a Z table, we use a student T table. And right now we are working on building what?
Confidence in it.
A confidence interval. Do you see anything that talks about confidence on this table?
Level.
On the bottom.
It should be on the top.
No, it should be, a lot of tables don't even have it on there. Okay? Because it's not necessary. Okay? So the only bit difference is here we looked up a Z tape value. See, when we use a T table, where did I put my magic pen? See, when we don't know alpha, we use this as a substitute, and we use a T table.
If we don't know the standard deviation.
If we don't know the standard deviation of the population. Thank you, okay. We use the t-table. Now with the t-table, we still need to know a couple of things. We need to know our alpha, and we need to know this thing that we call degrees of freedom. So we need to be able to work with those. Now, alpha we already know about. Alpha is the complement to our confidence level. So
What is that in
DF for degrees of freedom. And the degrees of freedom is simply n minus 1.
Oh.
Easy.
That's
One less than the n, huh?
That's from the variance, like, the denominator and the variance.
Similar. Okay. Now, the way what we use for degrees of freedoms varies from problems to problems depending on the tables that we use that has degrees of freedom. Do you see something on this T table that says degrees of freedom? Or DF?
No. Yes.
Yes, where do you find it?
Oh, yeah.
Oh, yeah, sorry.
It's the numbers that go down the left-hand column. Okay, and if you look at it, it starts at 1 and goes through what? Nope, it doesn't quite go through 1,000. There's not 1,000 lines on this table.
Oh, I thought
It cheats.
It goes to,
35.
29.
nope,
And there goes 30.
it goes to 30. And then what?
Add 10.
Then it goes to 40.
And 60.
And then 60. And then 80. Then 100. Then 1,000. What did I say when somebody asked about big numbers, big N's?
Oh, that was, you said.
I said a lot of people go ahead with 100, right?
100.
But some people think about 30.
30.
Okay? Some people use 40. Some people use 80. These tables will vary on what they do. Once we get above 30, the T table comes close to the Z table. And you notice at the very bottom it actually says
Wait.
Z.
Z. On the very bottom row it says Z.
Hey,
And why does
we
it
can
say
use
Z?
this for.
Huh?
And why does it say Z?
It has
Because when your N gets
90,
real big
80, 70.
and our degrees of freedom are big, if I have degrees of freedom, so if you look at degrees of freedom of 100, it gives you 0. For the first column, it gives you 0.677. If I use the Z for that value, I'd get 0.674. I'm within 3 thousandths. And you notice going all the way across, those numbers are fairly close. So the bigger the N gets, the more closer it gets to actually using the Z table. That's why I said if it's a big N, we don't even bother with this table, we just go to the Z table.
So the bigger the N gets, the bigger
The bigger the N gets, the closer it comes to, the bigger the degrees of freedom. And the degrees of freedom are based on the N minus 1, right? So it's going to come closer and closer to that. So that's sort of the aspect behind the way this table goes. Now, if you notice across the top, it talks about your alphas. And across the bottom, it talks about confidence intervals. Okay, if I have an 80% confidence interval, what's my alpha?
20.
20. If I'm doing a confidence interval, then I have to put half of the alpha in the top and half of the alpha in the bottom. If you look at the 80% confidence interval and you come up, what's half of alpha?
10.
10. You see that it's actually the same column. So see, some of them don't have the thing across the bottom that says confidence interval. You just have to know, I'm using half of alpha, so I'd go to T.10. And you just use that column.
Okay,
So,
you get 80% and then that's the 20%, so it's in the same column.
yeah, because half of alpha, when I'm doing confidence intervals, I always use half of alpha.
Right.
So the 80% column is the same as the 0.12. So you gotta it's just that aspect of it. Or if you look at it, two tails, it's 0.20. So that the top of the table has to do with alpha.
So I would just choose that Z 1.282 if that was the 80%? Or I have to look at the count minus one and choose one of these?
We have to look at the sample size.
So that in this case, it's like 39.
Well, I haven't done anything yet.
That's not the sample size?
Huh?
I thought it says the survey of 39 national flags.
Okay, now if I go and start looking at doing the problem. Where'd it go? So now I have to read and look at the problem that I'm doing. So this question says, the data in the table below are the results of a random sample of 39 national flags. And this is where we got to tie in some things that we did earlier in the class. Okay, it says from various countries. We are interested in finding a confidence interval for the mean of the colors of all national flags. So we're trying to find the mean of the population. We let X equal the number of colors on the flag, so there's either one color, 2, 3, 4, or 5. I guess that means no flags have more than 5 colors. Now, they presented our data in a frequency table. Huh? So now we have to be able to sit there and say, wow, what's the mean? No.
Take all of them
We gotta take out the
divided by
numbers.
5.
Huh?
Take all the numbers and divide by 5.
How do we calculate a mean?
The sum divided by
Sum
the
divided
number.
The sum divided by the
And
n. So my n is
39.
39.
Yeah.
So do we have all 39 numbers?
no.
No.
Not really. So there's a couple ways to do that.
We don't have all 39. It doesn't
We
have
make an
all
extra
39.
box.
This is where you have to, what do you mean you make an extra box?
Make an extra box.
But that equals 39, right?
Well, okay. If I add these up, it equals 39,
But we don't have this.
but we don't have the sum.
Oh, right.
You have to be able to sum them up,
Oh, right.
right?
Right, we have to get the relative frequency then.
So this is where I could sit there and say, well, I've got 1, 1. I've got what? 7 2s, 1, 2, 3, 4, 5, 6, 7. I've got 18 3s, 1, 2, 3, 4. I could do it this way.
That's what I did.
No.
I got it wrong.
Okay. So that's one way to do it. That would not be a very fun way to do it, especially if my sample was bigger than 39. So how else can we do this? Even using Excel, so we have 1 color, 2 color, 3 color, 4 color, 5 colors. These are my X's. And then these are my frequencies. So we have what? 1, 7, 18, 7, and 6. Does this somewhat look familiar to something that we've done in the past, hopefully? Yeah.
I don't know how to do it.
At
Huh?
least it looks familiar.
Yeah.
Yeah.
And as Abby pointed out, if I add these up,
30 now.
it adds up to the 39 countries that we were looking at, so our N is 39. So how can we find the mean? There's two different ways we can do it.
Help, so 39 divided by 5. And you're figuring out.
So you said what, 39 divided by 5? Which gives us what, 7 something?
7.8, yeah.
Yeah, do you think the mean's 7.8?
No,
No, why not?
because we don't have 7 flags.
Don't have 7 colors. The mean's gotta be somewhere between what? 1 and 5. Mean's gotta be in the middle, right?
How about 5 divided by 39?
We do quartiles.
Equals 5 divided by 39.
No.
0.128. That's even worse. That's a teeny tiny number, way less than 1.
Is that when we do relative or relative?
Well, one way we can do it is we can make a table and use all the different stuff. But there was, remember when we did the problem about the probabilities of people missing days of work? And we talked about probabilities and doing different things? We can use that aspect of that
So then, what
and sit there and say, well, what's the probability of X? So what's our probability of only one flag?
1.
Close. No, if it's a probability of 1, that means it's certain that all
Oh,
flags have one
0.01.
color. Close. How do we calculate a probability?
Frequency divided by the time.
Frequency it's the favorable outcomes divided by the total possible outcomes. So my total possible number of outcomes is 39, and one of them has one color, so it's going to be my X divided by the 39.
Isn't that like a relative, and then you do like cumulative relative, right?
Similar to a relative frequency, but it's a probability. If I'm calculating it, it's a probability. What is the Now, if I know that, so a relative frequency and a probability kind of give me the same thing. Just depending on what I'm talking about. So if I add this up, what do I get? Okay. Probability should always add up to 1.
Is it X or was it you multiplied by the frequency?
Yeah, it's the frequency. I clicked on the wrong box. Should be C. Wait.
It's the frequency, right?
I can't type in the formula. It is the frequency, but I typed in the number 27. It's the frequency divided by the king.
Yeah.
I clicked on the wrong box.
Yeah.
And then when I add that up, I should get,
Should I be able
One.
to write it down?
huh?
Use the absolute duplicate number thing.
No.
Okay.
You gotta put it in the same.
Can I do that with
The 39.
on the E?
Now, see, that's why I always sum columns, because we know that it, and I clicked on the wrong box. I clicked on column B instead of column C. This is why I do the quick addition to check it. What's my next column? We take the probability,
Minus W.
close,
And
times,
The frequency.
The frequency.
not the frequency,
The X.
That's
the
bar.
X. So I take the X value times the probability.
Yes.
And when I sum that column, I get 3.25641. So I'm going to say the mean color of flags on the sample of 39 nations was 3.256 colors. What does this 3.25 represent? The mean of what? No, it's the mean of the 39 nations that I looked at, which was a sample.
The mean of the 35 nations
That's right, yeah, we were doing this before.
flag, not my equity multiplied, just the nation.
The colors on the flags of the nation. Did you guys remember how to calculate this was all actually on the first test. You had to do this on the first test.
I did a terrible job on this, we have to do this?
Yep. This was the question that talked about how many days of work you missed or whatever. Same basic setup.
Yeah, I have to bust out on my name.
So now we need to get the standard deviation. And this is where you take your X minus what? No.
The probability of X.
When we're calculating variance, what do we subtract from the X?
And
What's the formula for a variance?
taking us back.
What's the formula for variance?
Denominator is n minus 1.
The sum of x minus x bar squared.
And since I wrote sigma here, would this be X bar?
This.
Since I wrote sigma here, this would not be X bar, this would be
So go to the top.
mu. I gotta keep my symbolisms correct. If I'd have written S squared, I could have written X bar.
Oh, yeah, yeah. Oh, my goodness.
So you remember Bronson said, everything we did on the first test, see, we still have to be able to calculate variances every time we deal with data. Now remember, we just have to take X minus X bar. So if I go back to this table, that's going to be X minus X bar squared times something. What am I going to multiply that by? What other column am I going to multiply by in this table?
The count minus
Not the count,
T.
The probability.
the probability.
And dragon. Okay.
So that means I'm going to take X, whoops, gotta put it in parentheses. X minus the mean, which I wanna lock down. And I want to square that. And then I want to multiply that by the probability.
Okay.
And when I drag that down and then sum it, what does this 1.011111 represent?
Mean, all the standard deviation.
No,
Variance.
the variance. This is the variance. Gotta remember, now, how do I get the standard deviation? I do what? Take the square root of the variance. So see, you still have to remember all those different aspects of calculating that. I could have gotten the mean without doing this table, but I couldn't have gotten the variance without doing the table. Well, yeah, I probably could have, if I'd have written everything out. Huh?
Mine says I'm wrong.
What do you mean it says you're wrong?
Well, my answer is 0.7280.
Okay, I'm gonna have to look at it because I need to go through and then figure out what you're doing wrong in your Apple.
Could you click G7?
G7.
Yes, that's where it's saying you're gonna put it, they just put some new number.
Did you put it in parentheses and square it? And did you lock down your mean?
No, I didn't put it in parentheses. It says 15.
Yeah, those parentheses are critical. Otherwise, all you're gonna square is your X bar. And it's gonna give you a real screwy number.
Oh, wait, I had to say right. Can you go back? Click again.
No,
Why is mine 37? Yeah, they put something wrong.
Where? Yeah, I do that. Wait.
if you can't get it that way, you gotta do it this way and list them all out. One, and then 1, 2, 3, 4, 5, 6, 7,
Click the wrong
and
one.
then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. How many was it? 18?
Yes.
And hope I counted right. I can highlight that to see if I did. So yeah, see down here it tells me I did type in 18 times. How many, and then what I had 4, how many times? 7? And I had, so I mean, if I can't get it using that table, I can list them all out. And then I can get my N, my mean, and my standard deviation by going equals count. And then I highlight all those numbers and this should come up to 39. I'm doing the count just to make sure that I got it right. And that goes from where? From J7 to J45 equals average, J7 to J45, and equals standard deviation, J7 to J45. I got all the 1.01. I should get 1.0. Yeah, 1.00557. Now, You notice when I did it completely, why did it come up a little bit different?
Maybe you forgot a number, or you added them.
So depending on how you calculate your standard deviation, it may vary a little bit. Remember I said sometimes we're going to get little differences in answers because of the way we calculate things? So those are the aspects behind it. But I have to be able to sort of look at that and play with it. So when I go back to my problem, what's my confidence level?
95.
95%. Okay. What was my mean? What was the mean that we just calculated?
3.256.
3.256, and it says round to what? 2 decimal places, so I'm going to round that to 3.26. What's my alpha divided by 2? That's my alpha. Should be able to do that one fairly quickly. 0.025. What's my alpha in the lower tail? 0.025.
Yeah, okay. Oh, so that's what the A
Oh,
was.
wait.
The mean.
That's alpha.
1837.
What?
1837.
Okay?
For what?
Now, I have to be able to add something here. This is going to be my error bound margin. To get my error bound margin, now the only difference is I still need a standard error and I need something from the table. But is my standard deviation of the population known or unknown? Unknown, so I'm going to use what? I'm going to use a T table instead of a Z table.
It's unknown even though we just got the standard deviation.
Huh?
It's so unknown even though we just got it from that,
What was that standard deviation of?
the sample.
Of the sample. So do we know the standard deviation of the population?
So we can't do that.
So we still can't, okay? See, we gotta keep going through that. So since we don't know the standard deviation of the population, we're going to use a T table. So, and when we use the T table, we need to know two things. We need to know our alpha divided by 2, but we also need to know our, what's that far column on the,
Oh, the confidence,
The DF,
DF, which stands for degrees of freedom. So we need those. Now this is where we're using the T table. I wish I wouldn't have done this, but we got to sort of do this in our tables. And this is going to cause you guys some angst. If I use my T table and I go down, do I have a degrees of freedom of 39? Wait, no, my N is 39. So my degrees of freedom would be
38.
38. Because remember, the degrees of freedom is equal to N minus 1.
Wait, is that T alpha
Alpha divided by
divided by
2. Huh?
divided by degrees of freedom?
No, alpha. Alpha always, half of it goes in my top tail, and half of it goes in my bottom tail. Now, this table is a little bit easier to use, because if I'm going with a 95% confidence level, I can just look across the bottom at 0.9 or at 95% confidence. And then I go up to my degrees of freedom, but here's where it doesn't give me a degrees of freedom for 38, so what am I going to use?
40.
I'm probably going to use the 40. So when I look this one up, where's my rag?
Doesn't even have 40.
Huh? So I'm going to use my t-table with alpha divided by 2 and degrees of freedom of 38. So in this particular case, what would I grab?
So freedom of 40.
2.021.
2.021.
What?
40.
95% confidence interval. 40 is closest to 38. Degrees of freedom is n minus 1. So there's my table value. Now I need to calculate my standard error. And since I don't know the standard error of the population, I'm going to use the estimate, which is equal to,
You said it.
the standard deviation that we calculated divided by, still divided by the same thing. What's it divided by?
Square root of count.
Square root of the count, or n.
Alpha is the divided by 2 is the 0.025.
Yeah.
0.0250 times the.
No, I don't, no, this just tells me what column I'm using in the table. If I don't have the table across, if I don't have this row across the bottom that says confidence level, and see a lot of tables don't have that row, then what I have to do is go and look up here where it says T of 0.975, because that would be subtracting 0.025, which has the 0.025 right below it for what's in my tail. And then I would come down and I would find that I'm in the exact same column, giving me my 2.021. So the table I gave you is kind of nice because it's got the confidence level in the bottom and you can come up. If you don't have that confidence level in the bottom, then you have to use your alpha in a single tail to come down. Okay, so depending on the t-table, so this t-table is a little bit nicer because it has that confidence across the bottom. So we have to go back and all that information that we gathered back here, so we get what? So our standard error was what? 1.0056
6, 5, 7.
divided by the square root of
And which is
5. What's 5?
what's the n?
the end.
5.
39.
39.
How many flags did we sample?
39.
We sampled the flags of 39 different countries. My sample size was 39.
Oh, I'm counting the things.
Which gives me 1 point what?
16102.
16102. So to get my error bar margin, I've got to take this number times that number.
0.16. Yeah.
Point one. What that?
0.16.
I can't read.
0.1610.
That's why you guys are punching it into your calculator. So 0.16102. See, this is where I'm going to come in here and say equals, take my standard deviation and divide it by the square root of 39.
Oh my gosh.
Okay? And then we looked at it, so this is my, what is that?
The estimate of a standard error.
The standard error estimate. Then I want to look at my t-table. My t-value for whatever, for 38 degrees of freedom, which we said was what? 2.021. So to get my error bound margin, what am I going to do? I need to get my error bound margin before I can do that, calculate the upper and lower. How do I get my error bound margin?
Is that the 0.3237?
Well, that's my standard error times my table value. See, this is why I say it's the same process, it's just, how do I get the standard error and where does the table value come from? So see, there's my standard error estimate, and there is my table value. So if I multiply those, there's my error bound margin. And then to get my lower bound, what am I going to do? To get the lower bound,
You take the mean and minus the error bound margin.
I take the mean and subtract the error bound margin. How do I get my upper bound?
You add it.
I take my mean and add the error bound margin. So I end up with what? Oh, shoot, I didn't put that to happen. I just want to slide this off enough that I can see those numbers and type this in. 2.93 and 3.58.
So unless you say to, like round 5 decimal, whatever, we should round to 2. Does that make sense?
You should round to wherever it tells you.
Oh yeah, okay, it does do that. I didn't, okay. Okay.
If it doesn't tell you, my recommendation is default to 4 if it doesn't tell you.
Okay, so I know in the thing that we just did, the extended one, sometimes it didn't say.
Yeah.
Okay.
and I didn't get to the proportion, which means that there's some problems, the last 4 problems or so on the homework. I don't know if I can go in and delete them or not.
Yes, you can.
Confidence interval?
Oh, yeah.
What did you say?
Huh?
I don't know what you're saying.
I said, I didn't get to the proportion one.
Oh, that's okay. Next time.
I didn't get to this one, but you have a homework assignment that assumed that I got to this.
You did it.
So there's gonna be like the last 3 or 4 problems
Mm-hmm.
that I didn't get to, so don't panic if you get to them.
Okay.
I will see if I can go in and delete them before you do it, but I don't know if since I've already scheduled it, if I can delete them.
Everything that don't look like we
So
did
if you
at
get to something and they start talking about a proportion, you can attempt to read the book and do it. It's not that much harder. You should be able to do it, part of it, even without doing this. What's the confidence level?
92, 1.92.
0.92, because they said a 92% confidence level, which means how much is in what's my alpha divided by 2?
4.
4?
Right, because it's 8% left over divided by 2, right?
So it would be what?
Point.
Oh, it'd be 8 divided by 2.
Point,
Oh, 0.08.
finish,
Oh, 0.4? Wait, 0.04.
0.04. And this one would be point. Now, the tricky part, the proportion. Now, we aren't talking about means, right? We're talking about proportions. And this says that they want the proportion of what? Construct a 92% confidence interval for the proportion of girls 8 to 12 beginning ice skating class. Well, how many girls do we have?
64.
How many boys?
16.
16. So what's the proportion of girls?
64 to 100?
No.
No.
If I'm calculating the proportion of girls, what do I have? We know that there's 64 girls, right? Out of how many children?
80.
Out of 80 children.
Oh.
Because I have
wrong.
64 girls and 16
wrong.
boys.
Yeah, I had wrong.
So I have, basically my proportion is 64 divided by 80, which is 0.8.
Point. I got a different number.
Huh?
Oh, 64.
64 divided by 80 is 80%.
64 divided by 80?
Yeah, because I have, how many girls?
64.
64.
How many boys?
16.
So how many kids do I have? 80 kids. What proportion of them are girls?
80%.
So see, even if you don't, even though we haven't done this one. Now, the only tricky part is, with this, it's kind of easy because we're still going to use the Z table. So that means we want to look up, if this is point, we need to look up the Z value for what? 0.04. So what's the Z value for 0.04?
3.303.
Wait.
I'm wrong.
Wait, are we looking
No,
on
I'm
the
wrong.
T table?
I'm wrong.
Oh, Z table.
Z table.
Oh my god.
It's a lot of things. I'm so confused.
So what's the Z value for the 0.4%.
There's somebody in that.
No, there's only one of them. Well, there's actually, huh?
I think it's 0.6554.
No, I think you looked up 0.4, not 0.04.
Oh, yeah, you're right.
Oh, I think I get that as well.
0.5160.
Nope. You're looking up a z-score, you're looking up the probability. Remember, we want to know the probability. This is the number from the meat of the table.
Negative 1.75.
Okay, 1.75. And I'm just going to use the absolute value of it. So I get my table value. So I get my alpha divided by 2, which in this case is 0.04, which was 1.7 what?
5.
5. I found 0.04 in this part of the table. And then I looked over to the column and up to the row to see what z value I got for that. Now the tricky part is, how do you calculate the standard error for this? And standard error is a little bit different than, because we don't have the mean, we don't have standard deviations. So when we calculate this standard error, and they may not use the word standard error precisely, but it's a square root. Most standard errors involve a square root. And it has a denominator of n. But what we get here is p prime times q prime. What's p prime and q prime? P prime is simply the proportion. So 0.8. You guys should remember what Q is. We talked about P's and Q's before. So if the proportion is 0.8, if P is 0.8, what's Q?
0.2.
0.2. They're the complements of one another. Remember when we talked about proportions, we always had the probability and the probability of it not being there. So sometimes you'll actually see people write this as 1 minus p prime. Remember we were doing that when we talked about other things? I said you'll see some people write 1 minus p prime, and some people will write q. Earlier in the book they were writing 1 minus p, now they're using q. When we talked about the binomial model. Now the aspect behind it is this is a model of the binomial model. What's our n? No, 80. Yep. The 64 kids plus the 64 girls plus the 16 boys is 80 kids. And when I do that, 0.8 times 0.2 equals 0.16 divided by 80 gives me 0.002, and then I have to take the square root of that. So what am I going to do? I'm going to take, remember, standard error times my table value. We'll have degrees of freedom on them. But see, every time I'm going to take my standard error times some table value. Just depends on what table I'm going to use and how I'm going to calculate the standard error. And I'm sorry, I went a little bit over, but I'll stop there. I actually did do that. So let me see. Times 1.75 gives me 0.78. So this would be 0.88. And then I take 0.72. And if I hit submit test, let's see if I get a bunch of green check marks. Again, like I said, the process is the same. It's just, how do I get standard error? How do I calculate this error? And they don't call it error bound margin in every case. When we deal with means, they call it error bound margins. When we deal with proportions, they call it EPB or EPM. I can't remember which they call it. But it's basically the same thing, the margin of error. And what does this mean? In this particular case, it means that I am 92% confident that the proportion for the population is between
7.72 and 0.88.
I know I wasn't going through that, but every time with an interval, I am 92% confident that the proportion of the population is between 0.72 and 0.88. If I go back and look at this problem, I am 95% confident that the mean colors of the national flags of all nations, or the population, is between 2.93 and 3.58. And for this one, I am 95% confident that the mean weight of newborn elephants is between 239.84 and 248.16 pounds. So if you have trouble with the proportions, that's fine, we'll work with that. Now, you had questions about how to do something on Excel.
No, I just didn't do the parentheses.
Okay,
That was it. It was just for this one.
yeah.
Because it has to be one, right?
But the steps are very similar. It's just where do we get the
For
different
the,
pieces?
the P,
Q,
yeah, for the P and Q. How come it was 0.3?
because it's the upper.
You gotta be able to distinguish the difference between
Does that
a
mean it has to be
sample
one,
and
right?
a population.
No, it doesn't matter.
Now,
It
you
is
see,
one
like in the
minus
early part of the
P.
semester, I'm so critical about that part of it.
You see, it's like, okay. Like
Okay, yeah, so
Like a coin,
when we.
heads and tails.
Yeah.
You have both heads and tails and it makes up a
This is more.
coin.
Point.
So when you have P and Q, it makes up the
Actually, the
whole.
questions that you do on the homework are very similar to this, except for in a lot of cases, when you start doing these problems, they're going to ask, they're going to mark it out in steps. They're going to give you this question, but they're not going to give you this picture. They're going to say, the first question they'll say, what is the standard deviation of the population? And then the next question will say, what's the standard deviation of the sample? Then the next question will say, what is the mean of the sample? So it will ask an individual question for each part, and then you have one final thing like this that gets you to illustrate it and show it out. So, like I did it, walking up to it and finding it piece by piece, where you had to find the standard error, they'll actually walk you through, like, this might be question 12, questions 5 through 11 will ask you for all the pieces that you need. And then question 12 is putting it all together. So when you start doing it, even though it looks like there's 33 questions, right. And when you get to this question, you should have already answered all the parts. And hopefully I will go through and have it set that if you use, instead of using something here, you use something just slightly off, that it won't tell you that you're absolutely wrong. Now remember, if you come up and you're within a couple of hundredths, don't assume that you're doing something wrong. Assume that you use maybe a wrong value, or you rounded someplace where you shouldn't have rounded, and it was a rounding error that looked at it. We can always look at that when you come back. If you actually write down your work or keep it in play, you can deal with it. Again, I'm going to use Excel as my calculator most of the time.
It'll find the score.
And actually, if I lose my tables, I can actually, the tables are all in Excel. It's just called norm inverse, or norm S inverse, or T inverse.
Instead of norm. T.
Well, if I'm using the T table.
Yeah.
Yeah,
Okay.
and then the inverse is always finding the table value given the probability.
Yeah, that's how I did mine.
Yeah. T, you gotta be a little bit careful because there'll be T for one tail and T for two tail.
Oh, I see. So you're looking for one tail.
Well, it depends. If I divide alpha by 2, then I'm using one tail.
Yeah.
If I just use all of alpha, then I use two tails. I think that's how, yeah. I always had to
That's
pay
how
attention.
this being said.
Yeah. See, because your T really looks at two tails or one tail, or, and it's not quite symmetrical. You can't look up the lower value. You got to look up what's in the tail, not in the body.
Oh,
It gives you it gives you what's in the tails, not what's in the body. The Z table gives you what's in the body, not what's in the tail.
that's right. Oh.
That's why they're slightly different.
Oh, I see.
So a lot of steps.
A whole lot of steps. I'll grant you that.
But it's on video, so we should be able
But the the steps are the same. It's just the pieces that we use varies depending on whether it's a proportion or a mean, and whether the standard deviation is known or unknown. And this one was kind of tricky because you had to go back and remember how to do that one. That was actually the question that we did back when we were doing the probabilities and the expected values. But like I said, I could list them out this way. But see, if I'd have listed them out this way when I calculated the standard deviation, I got something slightly different. So my answer would come up slightly different on my proportions. If you use your T inverse to get your T table values instead of the T table, the T inverse on Excel and also on the norm S inverse on Excel goes to like 9 decimal place accuracy, where these only go to 4 decimal place accuracy, so you will get a slight variance I tried to open it up to where it should calculate it correctly, but I don't know if I caught all the problems that use T-tables to expand give a little bit more tolerance. So if you're close, don't fret, I'll fix it. There are a lot of steps. It's if you round one or two numbers slightly different than carrying it all the way out full place, you can come up with answers that are slightly different. I'm done.
I'm done.
Get. There's nothing to